Okay, so we just explored our data and we understand a little bit better about how to construct our neural networks and what happens and what it means to have multiple neurons in a layer and also have multiple layers and also then to have this output layer. So we might as well just go ahead and build our neural network. So that's what this last lesson is. And I think you'll see that you really can understand in this real neural network using Pytorch, using a bunch of neurons, what's going on. So let's get to it. So the first thing we need to do is really change our runtime type. So we're in a Google Colab, and when you run a neural network, this can really take some time. Remember, our data set is 60,000 images that we're going to be training on. So we want this to be faster if possible. And instead of using the default, which is a CPU, that's what a lot of your operations on your computer is using, we can use a GPU, which when these dot products and matrix multiplication is occurring, they'll occur on a faster piece of hardware that originally was meant for graphics, but it can perform these operations as well. So in Colab, we want to go to runtime and then change runtime type. And normally it's set to none by default, so you'd have to switch it to GPU, and then you can click Save. All right. The next thing to do is to download our data. So remember, this is TensorFlow.keras. We're using this library, which Google Colab already has for you out of the box, and we're downloading our MNIST data set, and we're getting our X-train and Y-train data. And we'll talk about this part later on. And then it's a good idea to look at our data. So we can just look. Remember, this is all those images. Let's just make sure it's still a bunch of images. So we'll use matplotlib to display the first image, and that looks pretty good. All right, the next thing to do is to reshape our data. Why? Well, if you look at, we're working with this X-train data. If you look at what kind of data it is, remember this is coming through to us as a NumPy array. And what we want to do, we'll call this X-train tensor, is make a couple of changes to this. The first one is we want this to be a tensor, right? Not a NumPy array. So we have to import torch. Sorry about that. And then do torch.tensor. And now if we look at the data type, this should be of type. So I guess it's going to take a little while to do this, but this is now of type tensor. Okay, so we're now using Pytorch instead of the NumPy array. The next thing we want to do is, remember, we want to convert all of this into floats. And that we can see by doing .dtype. So now it should say float. Okay, that's looking pretty good. The last thing we want to do is, let's look at the shape of this. So remember, we have this issue, which is that it's giving us 60,000 images, but each one of these is a grid, right? And instead what we want is to unspool this so that we're not getting 28 different rows here, but one long unspooled vector. And the way that we can do that is, I think we should be able to do .view, remember, and we want to say we want 60,000 records. So we're going to go down from 3 dimensions down to 2 dimensions. And we're going to say Pytorch can calculate that 28 by 28 reduces to a vector of 784. And then let's confirm that by looking at the shape. So press Shift Return. So that looks pretty good, right? Now we have a vector of length 784. Let's maybe look at it. And we can see that it looks like a decimal, right? That's telling me that it's a float, and that's looking pretty good. So that's our X data, or our X train data. For our Y train data, we want to do something similar. Just comment that out. So we will take our Y train data. Again, if you look at the type, this is starting off as a NumPy array. So we want to convert this to a tensor. So we'll just do y train tensor equals y train, torch.tensor y train. All right, so that converts it to a tensor. Here with the feature data, that's a float, but really for our target values, remember what these target values are. These are the labels, right? This is like the numbers, 5 to indicate that this is a number 5. And so there's no decimal here, right? This is categorical data. Like it's either 5 or it isn't, right? It's not going to be 5.1. So the point is we don't want floats because floats are for decimals. And in fact, Pytorch will throw an error later on if we do use a float. So instead you use kind of the equivalent, Pytorch's equivalent of an integer, right? A whole number, and that's .long, okay? So we're going to convert this to be of type long, and we can confirm that by doing .dtype. And it says integer, which seems like we're on the right track. Okay, so we have converted this to of type long. All right, so we've done this part. We've reshaped our data. If you think about each one of these vectors, so we have x train tensor, and you select one, right? This is one long vector, which makes sense because what's next for us to do is do that vector matrix multiplication, right, of a layer in our neural network. Right? Remember that's going to apply the dot product to each one of our neurons with this feature vector. So if you think through this, each layer, we're going to take in a feature vector, right, representing all of our pixels, and it's going to be one row, 784 different columns, one for each pixel. And now each of those neurons has to be of length 784, right? Each of the feature vectors has to be of length 784, and you want 64 of them, one for each neuron. And each neuron also gets a bias, so we combine them into a vector, and that's why we have 1 by 64 here, right? 64 different entries, one for each neuron. Then we pass, so this will result in a 1 by 64 vector, right? Because we know the output is determined by the outer dimension, so 1 by 64 plus another vector of the same dimensions gives us a 1 by 64. And then we take this output and we pass it to our sigma function. That does not change the dimensions, it just takes these positive and negative numbers down to a range between 0 and 1. And then we take this output, this should actually be a lowercase a, because it's a vector. We take this output from here and we do another, right, vector matrix multiplication. And we get back a vector. Here, we pass through all of the outputs from the previous layer, so there's 64 different outputs, and we pass them to each one of the neurons in this layer. And remember, we want 10 neurons because this is our last layer, and we want 10 different outputs, right, a different prediction for each one of the possibilities, each one of those digits, 0 through 10. And we want our output to really be a probability, right? The probability that this image is the number 0, the probability that's the number 1, right? So to do that, we use the softmax function. Okay, now we've coerced our data, we've kind of explained what we want our neural network to be. Let's build it now. So we'll do net equals nn.sequential. We're just going to copy what's here above, right? We want a linear layer. That's that first layer above. We want it to take in 784 features and be consisting of 64 neurons. Then the next thing is to pass this to a sigmoid function. So these 64 outputs are passed to a sigmoid function. And then from here, we take, this is our first set of neurons, both the linear layer and the activation layer. Each of the outputs from this sigmoid function, those 64 outputs, we're then going to pass into our next linear layer. And we want this to take in 64 outputs from the previous layer. So take in 64 inputs, and then return 10 outputs, right? Those 10 values, one for each of the possibilities. And then finally, to convert this into probabilities and to accentuate or exaggerate the largest value, we use the softmax. And you have to do dimension equals 0. I'm not going to explain this. You can look that up if you want to. And then we just do net. And look at this. NN is not defined, so we'll say import torch.nn as nn. So we'll use that neural network module. And then the next thing I always like to do is now test this out once, right? Make sure that both our data is in the right format and our neural network is in the right format by passing in through some data. So here's my neural network, and we have this X train tensor 0. And what I'm looking for is just, does this not break? Does this return the right outputs? And it looks like it does. So by returning the right outputs, what I mean is, notice everything here is a valid probability, meaning they're all positive numbers, and they're all between 0 and 1. And there's 10 outcomes, it seems like to me, right? 10 outcomes, one for each of the possible digits. So this is a neural network taking in some data and making a prediction as to what digit it is, right? It's not trained yet, so these values they're not going to be right, but just making sure everything lines up from above. And the other thing we can confirm is that the sum of these possibilities, of these predictions, should equal 1. And that's true as well. So far so good, you know. Like even just getting this part right, I've at least messed it up many times before. So we've made a prediction, and then the next thing to do is to train our neural network. Oh, one last thing. If you want to kind of interpret this prediction, right, we get this output. Let's call this like y hat for now. Or I'll just call it prediction. If you want to see quickly, like what's the largest value, you can do torch.arg max, and this will give you back the index that's the largest. So here, I think it's, so we have options 0 through 9, and torch.arg max is saying 2 is the largest value. Let's just make sure that's true. So it gave us back 2. And that means that 0, 1, 2, this should be the largest. And it looks like it is. Okay, so if you want to see kind of what is our neural network predicting, it's predicting 2 above all these other possibilities. And we're finding that out by doing the Arg Max function, which just tells us which index has the highest value. All right, so we made a prediction. Next up is to train our neural network. Let's delete this, delete this, delete this. Okay, so this is a review from this earlier section. And remember what we need to do. Basically, when we train our neural network, we kind of see how off, we start with these random weights, and we want to then see what is the slope of the cost curve, and use that slope to then update our parameters. Before we just did one parameter. In the later lessons, it talks more about what it means for many, many parameters. But here, the concept is the same. So you need to, see what is the slope of the cost curve at these initial random parameters, and then use that slope to tell us how to update those parameters. So doing that involves some steps, because to calculate the slope of the cost curve, you need to calculate the cost at those initial parameters. And to calculate the cost, you need to calculate, the prediction compared to the actual value. So remember, we have those actual values. Those are our y train tensor data. Okay, so let's do this. So we want to calculate, first make the prediction. So we kind of did that above by passing through this. We'll do this above. Okay, so this is my y hat, right? And we make the prediction, and then that gives us back these 10 values. The next thing we want to do is use the loss function. And I'll just skip ahead real fast. Once we calculate the loss, then we want to, this loss function is pretty smart. It knows also how to calculate the slope at that loss. Okay, so one thing that's going to be different is that our loss function, previously we did nn.msc loss. right? That was our loss function. This time around, we're going to do cross entropy loss. So we're kind of this is going to be what we'll call our criterion. So we're taking this tool off the shelf. Now, remember previously what MSE loss did was it basically said, okay, here's the actual value. This actually was the number 5. And here we'll do minus the expected. And then when you remember, we squared it. We squared the error. And then divided by the number of observations. The cross entropy loss operates very similarly. It also is essentially looking at how much do we deviate? Does the actual value deviate from the expected value? One thing that's probably confusing to you is, well, okay, the actual value is that this y train tensor was like, the number 5 for this first observation. So that I guess we understand. But the expected value seemed to be like all these digits. The way cross entropy loss works is it will just look at that corresponding index. So it'll be like, oh, we saw a 5, and we are going to instead, the value that we're going to look at for the prediction is 0, 1, 2, 3, 4, 5, is this value. So it's essentially going to look at this and say, oh, the real 5 was a 1. This actually was a 5. So that index of being a 5, when I look at it, you are only saying there's a 10% chance. So I'm going to highly penalize that because you are far away from that value. Okay? So it does have a formula like pretty similar for doing the actual minus expected. It takes that 5 and it says, oh, it actually was a 5 with 100%. That's what it was. And now let's go to that index and see what you predicted. And that's how we do actual minus expected. And like I said, this isn't exactly, it's a little bit different beyond that, but essentially it's calculating the distance between what had actually occurred and what you expected, what you predicted it was. All right, so that's our cross entropy loss. And then the next thing for us to do is remember the learning rate. So remember, when we update this, we don't update it like exactly by the slope, but rather use a learning rate. And for this, we'll do from torch dot optim. Yeah, optim. We do optim dot atom, I think. I'll say import torch.optim as optim. And then here we'll do optim.atom, and this is good. So we need to pass through what? Well, we need to pass through the parameters of our neural network, and we also should pass through a learning rate. And we'll do that 0.005, I think, is the value. And we can call this my optimizer, and that's pretty good. And this has sequential object, has no attribute params. Is it parameters? Sorry about that. Yeah, it's parameters. Okay, so now we have kind of taken these two tools off the shelf, and we still need to now go through this. So we made our prediction. What's next? We need to calculate the loss. Let's move this down, actually. All right, and let's move this down as well. Okay, so we made the prediction, y hat. We want to calculate the loss. So the loss, we call it our criterion, and we'll use the same formula we see here. We'll do actually expected y hat, comma, y tensor. So this is what it should be y train tensor. This is what we actually observed. And this is the first prediction. When we did net x train tensor, we are only passing through, right, one single observation. So this y hat should just be like, for one prediction. And that means we don't want to pass, here we should also just pass through one, is the point. One single label, right, like the number 5. And now we can use that cross entropy loss to compare what we predicted versus, the number 5. And that'll be our loss. And then we'll do loss.backward. So why are we doing that? So this step here, this calculates the loss, like where we are on the cost curve, and this loss.backward calculates the slope of the loss. Okay, let's see if that works. I knew I would break it. Expected dimension. I think the reason why is, and I just know this by trial and error, I think you have to convert this back to be be like basically wrap this in another dimension, make this back to be two-dimensional, and I think that might work. Let's see if that works. This might break again. I'm just gonna have to cheat at this point. Sorry about that. Yeah, so you see this prediction.view 1 by 10, and here we're slicing the first entry. So it's keeping this actually, we'll just copy this. So you can see this is really the formula that that we're using. So it's the same thing. We're just changing the dimensions slightly. So what we're doing, apparently for this loss function, we can't just pass through a single vector. So if you think about what Y-trained tensor is, previously I was just selecting one entry. Instead I'm going to pass through a list. So this is like, an entry in a list. And it's the same thing with the prediction. The prediction originally, this y hat right here, let's just take a look at it. This is, one prediction, but we want to, just like we have this guy wrapped in a list, right, this was like thing 5, we're also going to wrap this in a list. And the way to do that is apparently to do view, let me just copy it, 1, 10, 1, 10. So now you'll see the difference. See, this is wrapped in an extra list. That's all we need to do. So this is my expected, and then this is, we're gonna slice this guy right here, all right? And then we'll do loss.backward, and that works. Okay, so we just had to slightly change the dimensions. And then from there, the last step to do is opt.step. So now that we've calculated, so previously we calculated the cost, where we were on the cost curve, and the whole point of that was to calculate the slope of the cost curve. Now that we calculated the slope of the cost curve, we can take our next step by doing opt.step, and that worked. Okay, so we just performed gradient descent one time here. What we want to do really is perform this, again and again and again and again to descend along this cost curve. Okay, so that's what we'll do next. So I do that in this putting it all together section, meaning that I'm just gonna quickly, run through the code, and I have this so that, if you want to, you can just see all the steps, in a condensed format. So here we download the data. We need to specify to use the graphical processing unit. So we did change it, but to actually use it with our tensors in Pytorch, you have to specify you're doing that. And here you do that with CUDA. So we'll see this takes a second. See that? It's like converting all these somehow to be used with the GPU. So this is like, I guess, faster tensors. Then we will define the neural network. So this is exactly what we did before, but the same thing. We also need to convert all these numbers to be used with the GPU. So you have to call net.CUDA, and that's it. Now, this is just what we saw before. We are passing through our neural nets parameters, specifying the learning rate, and also using this cross entropy loss. And then here what we're doing is we're going through, pairing together our X-trained tensor GPUs and the corresponding label. So these are all those features, the corresponding labels. So this is that big X vector and the corresponding Y value. Let's talk about this in a second. We'll make the prediction, and then we're back to that annoying prediction view thing. We have to change that. But we're calculating the loss using cross entropy, and then we are calculating the slope, and then we are finally taking a step. I called this atom. It doesn't matter. We can call it opt, which is what we used previously. That's fine. And then finally we are printing out the loss. And this is running. Now we don't see anything below, so maybe we wouldn't know that it's running. But you can see that this green arrow is showing us, it is moving through the loop. The other thing you can see is it's executing the cell. Like, look at this, going through linear and softmax and cross entropy down here. So you can see that it is happening. So just to remind ourselves what's happening below, we are looping through our data. We are making a prediction. We are calculating the loss. We are calculating the slope of the at that loss, and we are then updating our parameters. A couple of things to explain. What is this net.0 grad? When you calculate the loss here, when you do loss.backward and calculate the slope of the cost function, okay? That slope is stored, believe it or not, on these tensors, I think. So it's stored on like our X tensor, and that's what's going to be used to then make the next step, right? Is this loss, these slopes. The zero grad zeroes out those slopes so that we can, in the next iteration, the next time, we can start all over again. Now with these updated parameters, make the prediction, calculate the loss, calculate the slope of that loss, and then update our parameters. Do it again. Now make sure we kind of reset wipe the slate clean by clearing off all those slopes. That's what this line does. It clears off all those slopes. Okay, so then we can make the prediction, calculate the slope at these new parameter values. Okay, so that's what's occurring. One other thing to explain while we're waiting is you notice we said for epoch in range 3. That's saying go through the entire data set 3 times. Okay, so that's what's happening while we wait, and we'll come back in a second when this thing is all done. Okay, so our neural network, it looks like, has finished training, so that's good. And one other thing to talk about is, remember I kept promising that we would talk about this test data. So what is the test data? Well, if you think about what we did with our neural network, what we kept doing was feeding our neural network data, these images, telling it the answer, right? We're telling it, hey, this is, here's all the features, make your prediction, this was the number 5. Okay, here's all the features, make your prediction, this was the number 2. And we're having our neural network then, calculate how far off it was and keep responding, right? Keep updating the parameters. Now, one issue with doing this in machine learning is kind of like, well, how do we know our neural network didn't just do a good job of understanding and interpreting these particular handwritten digits and kind of like memorize, oh, this is a number 5. But if I slightly change my number 5, then it's not going to do a good job with, future data. So in other words, what about data where it does not have the answers? We are concerned that our neural network may have just memorized all of these number 5s and knows how to predict them, but maybe going forward with data it has not yet seen, it doesn't know how to predict new data, right? New data. And that's really what we care about, right? We care about going forward. How does it do on data it has not yet seen? So this problem is solved very cleverly in machine learning by having a test set. So this is what this is. If you look at the X test data, this is another 10,000 images that I guess we have not reshaped yet. But these are images that we have not trained our neural network on, right? And the whole important thing about this is now we can say, okay, our neural network has seen this set of data, this 60,000 images, but we don't care how well it does on images it's seen and knows the answers to. Right? We've told it the answer. What we care about is how well does our neural network make predictions when it does not know the answer. So what we do is we take our test data, we convert it, this is us just converting it to a tensor again. Because remember, we start off as a grid, and really as a NumPy array. So we convert it to a tensor. We then convert this to a vector, right, of length 784, and convert this to a float, and then also make sure we're using the GPU. And then we say, give us your prediction for the test. Okay, so this, if you look at this, these are a bunch of predictions of probabilities. It doesn't look like it, but probabilities of how likely do you think this first guy, maybe we'll just look at one of them to make it more clear. How likely do you think it was for this first guy to be the number 0? How likely do you think it was for this first image to have been the number 1, and etc. And if you want to kind of see, turn this into hard labels, like what did you most think this image was? Well, remember, we can use our Arg Max function, why can't I speak, to see what value was the highest. And that's not right. Let's do, so sorry about that. Let's just select the first one and say, yeah, I think that should do it. Okay, so here it thinks that it's number 7. Number 7, apparently, the seventh index was the highest here. 0, 1, 2, 3, 4, 5, 6, 7. So it thinks that this was the number 7. And if we look, I guess, plt.imshow of this first digit, bracket 0, we cannot see it. Oh, because it's a NumPy array. Let's just take this. X test bracket 0. It looks like the number 7. So this made a really good prediction, right? The highest number that it predicted by doing torch arg max was the number 7. And that's what it predicted. And that's what it seems like this is. Now we want to find the arg max, perhaps, of all of our data. And the way that we do that is we can pass through, say, look at predictions test and set the axis equal to 1. The 1, it means it's kind of going down, it's looking across each column and finding the arg max, because if you think about what this predictions test is, you know, it's a tensor of predictions for all those digits, but we have them for every single observation. So this is for 2 observations. So we want to specify, hey, find the arg max this way, you know, horizontally, not vertically. Okay, so that's what this 1 is doing. And if we do that, then you can see now we're getting these hard predictions. This is the highest number from each one of these. Okay, this is the highest. Which index is the highest out of each of these predictions? That's what our neural network is predicting effectively. And we can compare it against the actual data. What's weird is it says 9. Oh, there it is, 721041459, right? So it isn't getting it perfect. This one is off, but it looks pretty good. And if we want to see how well it does overall, we can use this accuracy score. And this basically is just, okay, what percentage of these predictions matches the test data? So again, this is data that we have, that our neural network has not seen before, and now we're gonna, you know, compare its predictions versus the answers and see how well we did. And I don't know. Oh, we did pretty well. All right, so that's it. That's a neural network. Once again, you can go through, not this, you can go through the free curriculum and take a look, and it has all this in there, and kind of move through those steps. And if you can understand that, you're really understanding a lot of things there. The only thing left is really understanding, you know, what does it mean to descend down a cost curve where there's not just one parameter, one weight, but like tons of weights. Okay, so yeah, this has been great work. Good job, and keep going.